Sitara, as we call him, invited, said that this is a lecture mainly intended for students, and so to be fair, students should be asked, allowed to ask some questions, but since they will have an opportunity to talk to him during the coffee break, so we will postpone they can postpone asking questions till the coffee break. The next speaker is Shagato Ray, who is also a student of Somesh Bagchi, his second student in fact, and he is going to talk about some work of Somesh Bagchi connected with the uncertainty principle.
How does one? And this is. And how does one use the pointer? Center. I first thank the organizers for organizing a beautiful conference here in Chennai. I also thank the organizers for dedicating a session of this conference to in a memory of Professor Somesh Bagchi. I'm going to talk to you regarding his SCB's work on regarding uncertainty principle. But when I started to make my slides, I found out that there are so many people involved in this work. I mean, lots of friends are here. So I thought that it's better to try to give a short survey of activity regarding uncertainty principle, which I knew as a PhD student. I joined ISI Calcutta in 1993 and started working with Professor Bagchi around beginning of 1995. And then in 1995, there was a discussion meeting in Delhi University. And in that, Professor Sitaram gave a talk on uncertainty principle. That was my first introduction to uncertainty principle. And he talked about a lovely theorem, which I found very interesting, came back to Calcutta and started talking to Professor Bagchi. And he also became interested, and we started looking at results of that kind. So the story starts with the theorem of Hardy, proved in 1933. So to explain the theorem, I need to describe what is the definition of Fourier transform, which sounds funny. So if f is an L1 function, you define f at y without using 2 pi. That's important because the theorem depends on that. So the theorem of Hardy says that if you have a measurable function where f has a Gaussian decay by e power minus ax square, and the Fourier transform decays like e power minus by square. If AB is bigger than 1/4, then f is 0. So that is an uncertainty principle that both cannot have a very fast decay. But the second statement is also equally beautiful, that if AB is 1/4, then it characterizes the Gaussian, that there is no other function except constant multiple of the Gaussian. As I know, I mean, during that time when I first looked at that theorem, there were only 2 books where this theorem was available, except of course the paper of Hardy, which I didn't have access to because MathSciNet was not available those days, neither the Journal of London Math Society went digital. The only 2 books which had this theorem one was Deem and Mackin, and the other was by Kumarvelu Chandrasekharan. That was a Springer book called Classical Fourier Transform. And now there are 2 other books. Even Stein and Saccacci complex analysis book has this theorem as an exercise. Anyway, the case n equal to 1 was actually proved by Hardy in 1933. And the extension to n bigger than or equal to 2 was by Sitaram, Sundari and Thangavelu in 1995. And In 1995 discussion meeting, Sitaram actually talked about this. It was reported in 1995 discussion meeting when I first came to know of it. The crucial point in this theorem is actually to prove two, that is the characterization of the Gaussian. And then one actually follows from it by using a simple scaling argument. Anyway, Hardy's theorem was later generalized by Michael Cowling and J.F. Price, that's in 1983. They replaced the pointwise decay of f and f hat by average decay. What I mean is a statement like this, that you have a function, measurable function, you choose pq in 1 infinity. Here p and q are not dual to each other, just arbitrary indices. You just have to assume that one of them is less than infinity because you don't want to land up with Hardy's theorem. Now, if for some a and b positive, the LP norm of e power a mod x squared times f is finite. Since e power a mod x square grows very fast at infinity and still it is in LP, that means f must be having a decay around infinity, but it's measured in average of LP norm. And a similar condition on f hat, where you put e power b mod y square. If both these are finite, then AB bigger than or equals to 1/4 actually implies that f is equal to 0. Hardy's theorem, the original proof of Hardy actually uses classical complex analysis, mainly Fragment-Lindelof theorem, and so was the case with the theorem of Cowling and Price. They have actually proved some complex analytic lemmas which were relevant for their case and got a statement like this. And it's not very difficult to see that the statement of Hardy can actually be deduced from that of the statement of Cowling and Price, because the condition is more generally we are using average decay instead of pointwise decay. The case n equal to 1 was actually proved by Cowling and Price, and then SCB and myself we did the height dimensional extension. It was not very complicated. The case AB bigger than 1/4 of Hardy's theorem follows from the theorem above, which is expected, but SCB could come up with a surprising observation using some very simple convolution trick, that the case AB bigger than 1/4 of the Cowling-Price theorem actually can be proved using the theorem of Hardy on pointwise decay. So the average decay version actually follows from the pointwise decay version, but it applies only to the case AB strictly bigger than 1/4. As you can see in the statement of Cowling and Price, AB equal to 1/4 case is different from that of Hardy. This theorem is not characterizing Gaussian. Anyway, this observation of SCB turned out to be handy. We could push this method to certain other cases. So the next question is possibility of characterizing the Gaussian using the average decay like Cowling and Price did, not the Hardy. So answer to this question was provided by SCB in 2000, which he didn't publish at all. The statement is something like this, that suppose for some a and b positive, the numerator is exactly what Cowling and Price used, but you divide by a polynomial, because if you want f to be a Gaussian, that would cancel the other factor. So you need something to make the chap integrable, so you have to throw in a polynomial. So that's what he did. And the Fourier transform satisfy an analogous condition, that mod f at y power q whole power bq norm y square, and then again you divide by a polynomial. If both these are finite, and if AB is strictly bigger than 1/4, then f is 0, so uncertainty is still there, but if AB equals to 1/4, then f is a polynomial times Gaussian. That was possible. Now, if you could manipulate properly the power of the polynomial appearing in the integrals, you can actually characterize Gaussian by dropping the polynomial. That is not very difficult. You just have to choose correct k and l. But SCB didn't publish this. I will tell you the reason why that happened. The timing is actually very important. At the same point of time, around 2000, a similar development was taking place in France. This was related to a theorem proved by Arne Beurling, and we knew absolutely nothing about that. It was actually Professor Shobha Madan of IIT Kanpur. She was visiting Orleans at that time, and from there she sent us a mail saying that some of her friends proved a result which is actually a generalization of the result which SCB proved, and they were writing it in the form of a paper at that point of time. Anyway, that is related to Berling's theorem, which I am planning to come to. The collected works of Berling contains a theorem without proof, which generalizes the result of Hardy and of Cowling and Price. A proof of this theorem was later provided by Lars Hermander in 1991. I remember explaining this in ISI Bangalore colloquium or something around 1995 when I was visiting there as a student. This was also a hardcore complex analysis result. This theorem proves an uncertainty principle using joint decay of f and its Fourier transform. However, it did not deal with the characterization of Gaussian, that is the case AB equals to 1/4. So what is the statement of Berling's theorem? Well, the statement is this, that suppose f is an L1 function and you look at this double integral mod fx mod f at y e power mod xy dx dy is finite, it then follows that f is 0. We don't know whether Berling actually knew about the statement of Hardy's theorem. That has never been mentioned because he has never written it as a paper. However, Hermander perhaps refers it. I'm not very sure. This theorem implies the case AB bigger than 1/4 of the theorems of Hardy and of Cowling and Price. So we were naturally interested in the higher dimensional generalization of this result, but it required an interpretation of the quantity mod xy. What should it be in the higher dimension? So two obvious alternatives were you look at norm x times norm y, or you look at modulus of the inner product of x and y. So SCB and myself could prove the version where you put e power norm x norm y, and then Narayanan could come up with a proof where he used the weaker condition that e power mod inner product xy dx dy is finite. That implies f is 0. Narayanan used a Redon transform to reduce the problem to one dimension, a technique which will be used by several people in different contexts later, but I should mention at this point that the higher dimensional version of Hardy's theorem, which was proved by Sitaram Sundari and Thangavelu in their Proceedings Indian Academy of Science paper, I remember they have also used Redon transform first, and then they generalized the proof. So the use of Redon transform was already there in the context of extension of Hardy's theorem in several variables. Now the search was on for the characterization of Gaussian in the framework of Berling's theorem. So that is the case AB equals to 1/4. And then Aline Bonamy, Philippe Gemma, and Bruno Demange, they answered all these questions in the framework of a single theorem, generalizing Berling's theorem in 2000. That was the same year when SCB also came up with this proof of characterizing Gaussian, but he was a little late. So the statement of the theorem of Bonamy, Gemma, and Demange is the following, that the numerator is same as in the higher dimensional analog of Berling's theorem, but you have to divide by a polynomial, which was to be expected. Then you look at 1 plus norm x plus norm y power n in the denominator, and then f turns out to be 0 when this capital N is less than the dimension. If this capital N is bigger than the dimension, then the above relation holds if and only if f can be written in the form fx equals to a polynomial times e power minus half mod xy, inner product xy. Actually, their version is, I have missed some a here. There should be an a appearing here. Axy should be there. Sorry. So A is a real positive definite symmetric matrix. Now all the previous theorems discussed here follows actually from this result. In particular, this implies the Gaussian characterization proved by SCB. So that is the reason why he didn't publish it. Anyway, the case, as I mentioned already, the case AB equal to 1/4 of Hardy's theorem is really a theorem about entire functions of order 2. You just look at the Fourier transform and look at the complex analytic extension. In fact, the theorem amounts to saying that if capital F is an entire function of order 2 and type B that decays like e power minus by square, which is actually supplied by the Fourier transform when restricted to R, then Fz is actually e power minus bz square. So it's a simple complex analysis lemma. Now all the subsequent generalizations of Hardy's theorem actually relies on this complex analytic extension of f hat and the relevant complex analysis in some way or the other. it actually indicates that the theorem should be valid in a more wider context of Fourier-like transforms, not specifically about Fourier transform. This was persuaded by several people, which we shall indicate in the due course in the context of Lie groups actually. However, it is worth pointing out that in 2010, Michael Cowling and then Escuriazia, I am not very sure about my pronunciation, I must be wrong, Carlos Koenig, Ponce and Louis Vega, they provided real variable proof of various forms of the uncertainty principle by reinterpreting these results as uniqueness theorems for the solutions to Schrodinger equations. This is one question which Sundari was asking for quite some time, that can one provide a real variable proof of Hardy's theorem without using complex analysis. That has finally been achieved in 2010. And then people were interested in extending it to non-commutative groups. So first came the nilpotent Lie groups, where the typical problem of complex analytic extension was quite involved, because you cannot really have complex analytic extension of the Fourier transform, so something else had to be done. So the first case was on the Heisenberg group, which is a prototype of a nilpotent Lie group. So I will just explain those symbols which is required to state the theorem. So for Heisenberg group, the support of the Plancherel measure can essentially be parameterized by r minus 0, where corresponding to any lambda you have the Schrodinger representations pi lambda. These representations act on the Hilbert space L2 of Rn. And the statement of Hardy's theorem for Heisenberg group appeared in the paper of Sitaram Sundari and Thangavelu in 1995 in Proceedings Indian Academy of Science. I remember all these things because as a PhD student I was reading those papers between the line, because I was trying to copy those arguments to write new papers. So suppose f is a function on the Heisenberg group and a and b are positive real numbers. Suppose you have a decay like this on f, that means mod fxy t is dominated by gxy times e power minus at square. So decay is really on the central variable. And the Fourier transform, which is a Hilbert-Schmidt operator on L2, the Hilbert-Schmidt norm decays like e power minus b lambda square. If ab is bigger than 1/4, then f is 0. That is the most natural analog which one could think of. However, Thangavelu later had many more refined versions of this, because this one has the problem of depending too much only on the central variable. This was later generalized by Sundari, Cowling, Francesca Astengo and Bianca Di Blasio, if I am correct, for two-step groups in 2000 again. And then Kanyuth and Ajay Kumar, they extended it for simply connected nilpotent Lie groups in 2001. And then by Ali Bakloti and Kanyuth for connected nilpotent Lie groups in 2008. Okay. We were interested in proving then a version of Cowling-Price theorem for simply connected two-step nilpotent Lie groups. Actually, what happened during that time, a book on representation theory of nilpotent Lie groups by Corwin and Greenleaf had just come out, and I thought that maybe I can crack this book. So I started reading, found it quite difficult. After 3-4 months, came down to two-step nilpotent Lie groups, and that much we could manage, because I was interested in Kirillov theory those days very much. So this theorem, this Cowling-Price theorem actually sort of was related to that, because a nice parametrization of the support of the Plancherel measure was needed, because I wanted to put an integral decay condition on the Fourier transform in this case. So you needed to know what exactly the dual looks like and what is the Plancherel measure. It's not that it was not known, but it was given in a form which was very complicated to understand. So I wanted to have a simpler proof in a simpler case. So this was actually achieved by using the orbit method of Kirillov, and SCB found it actually very interesting. I mean, going through this exercise of simplifying things and understanding each and every line of how Kirillov theory is applied to the two-step case, what is the structure of coadjoint orbit, things like that. He found it very exciting. So, so little bit about structure of two-step group, just the definition. It's simply an Euclidean space. You can think of it as R of n plus m, and you have a non-degenerate map from Rn plus Rn to Rm. Compared to this map B, you can actually define a group structure on G. It is simply given by Vz dot V prime Z prime is equals to V plus V prime, that is in the non-central variable. In the central variable, it is Z plus Z prime plus half B V V prime, which is the twist. In the case of Heisenberg group, it comes from the canonical symplectic form. Now, what we could show that G hat can be essentially parameterized by a linear subspace V of G star. G star is the real dual of the Lie algebra G. Essentially what happens is, from this G star, inside G star you can actually find a vector subspace, and that from vector subspace you have to delete 0 set of certain polynomial. Then the remaining set, which is the set of full measure, is actually support of the Plancherel measure. And the polynomial whose 0 set you have to delete is actually the so-called Puffian, which gives rise to the Plancherel measure in the case of two-step groups. So I have written simply it as d mu lambda. This is actually the Puffian, and lambda is a linear functional here. Anyway, just to understand the statement, all this is not required. So suppose f is a function in L1G intersection L2G, and suppose for some positive real numbers a and b, you have a Cowling price kind of decay on the function, which is possible because G is essentially a Euclidean space. And then on the Fourier transform, you put this kind of a decay. This norm lambda does make sense because V can be identified to an Euclidean space. It is simply a vector subspace of G star. And then you get the uncertainty. If AB is bigger than 1/4, then F is actually 0. Later, Ali Baklauti, Eberhard Kanyuth, then of course Thangavelu, then Sanjay Parui, they have proved more refined versions for more general nilpotent Lie groups, but I don't know much about those results, so I can't comment on that. Next, the interest shifted to semi-simple Lie groups. So G stands for a connected non-compact semi-simple Lie group with finite center. A typical example for us is SL2R. Now for G you have the Kartha decomposition K F plus bar K, where K is a maximal compact subgroup of G and A is abelian. For G equals to SL2R, it's easy. This K is isomorphic to circle, A is isomorphic to R, and A plus bar turns out to be closed 0 infinity. It's the positive Weil chamber. AM is the centralizer of A in K, and for SL2R we actually have M equals to plus minus identity. And to define the Fourier transform here, I will rely again on principal series representation, but no longer class 1 principal series. So principal series is parameterized by what should I say, the complex valued real linear functionals on the Lie algebra A, so AC star, and sigma belongs to M hat. That means sigma is an irreducible unitary representation of M. So the principal series representation is parameterized by lambda and sigma. These are actually induced representation, induced from the minimal parabolic. For SL2R picture, the situation is much simpler. Here lambda is simply in C, and instead of this sigma, you simply have plus minus 1. When lambda is in A star, then we know that this pi lambda sigma G, these are unitary operators on certain Hilbert spaces H lambda sigma. We don't need explicit expression of that right now to understand the statement of the theorem. So this theorem was actually proved by Cowling, Sitaram and Sundari. Actually before that they had written one paper, Sitaram and Sundari had written a paper in Pacific J-Math, but I have forgotten which year was that. There they had one condition on G, that G have only one conjugacy class of Kartha subgroup. That was perhaps required because they couldn't take care of the other series of representations except principal series representation, and it was not very clear at that moment that if Fourier transform of a function vanishes on the complexified principal series, does that really imply that f is 0? Am I correct, sir? Was that the confusion at that point of time? Okay. For semi-simple Lie groups with one conjugacy class of Kartha subgroups, these pi lambda sigmas are actually enough to understand functions. So they had one theorem, and then came input from Michael Cowling. They have this result that if f is a measurable function having a decay essentially on this A part, which is an Euclidean space, this T is parameterized by Rn, so this is the norm which you see. And then the Hilbert-Schmidt norm of f hat is dominated by e power minus b sigma norm lambda square for all sigma in M hat. That condition is a must. If AB sigma bigger than 1/4 for all sigma again, then f is actually 0. So that was interesting that they could actually show that the Fourier transform f hat is actually 0 for pi lambda sigma for all lambda in AC star and for all sigma in M hat. That essentially implies that if is 0, you don't need other representations. That had something to do with Harishchandra's subrepresentation theorem. Okay. Now, more refined versions were proved later by Narayanan, Rudra Sarkar, S. Thangavelu, and I had some contribution in that. Okay. So, at that point of time, some of us felt that there should be an analog of AB equal to 1/4 also. What happens to that case? Everybody is talking about AB bigger than 1/4, because as you know, as a PhD student, you are simply looking for problems. And then somebody told me that this AB equal to 1/4 case is just an Euclidean accident. You cannot expect such things to happen on Lie groups. So me and Narayanan, I remember once we were running all those calculations and trying to see whether all the estimates which has been used in the proof are sharp. We found out that it doesn't look quite sharp, because sort of people are trying to ignoring the fact that the volume grows exponentially here, and the spherical functions have sort of a half decay. That had to be incorporated in some sense or the other. If you do that, then something better can happen. So that's the simple thing we wanted to do. And as a result, we needed to know what is heat kernel on the group. Actually, what it happens that in the case AB equals to 1/4, one can characterize heat kernel of the symmetric space G mod K, which is the most natural analog of the Gaussian. So for that, what we did was we had to forget the group case. We had to concentrate more on functions which are right K invariant under the action of K. And for that, instead of the group Fourier transform, one can actually rely on a more geometric Fourier transform which used by Helgason and usually known as Helgason Fourier transform. So I have given the definition here. So what happens is if F is right K invariant, then one knows that the class 1 principal series pi lambda 1 is the only relevant representation. That means sigma coming from M hat becomes trivial. So if you look at F hat pi lambda, that is an operator on L2 K mod M, apply it on the constant function 1, it is again a function on K mod M, evaluate it at K, that is actually F tilde lambda K. There are other ways of explaining this in terms of the plane waves, but let's not get into that. So this is a sort of an analog of, as I have written here, this is analogous to writing the Fourier transform simply in polar coordinates. Now, on G by K, one has the standard heat equation that Laplacian of uxt is del del t of uxt, ux0 is fx, then uxt is known to be a convolution with respect to a radial kernel, that is the heat kernel. So uxt is f convolve ht, where we know that the Fourier transform of ht is actually Gaussian. So if you go back to Hardy's theorem, in the AB equals to 1/4 case, if you look at the proof of Hardy's theorem, what Hardy actually has done, he has characterized the Fourier transform as Gaussian. And then it was an Euclidean accident that the function is Gaussian. So in this case, what you can do is that the Fourier transform is actually Gaussian, and then the function is the heat kernel. That's the idea we had. But then Professor Sitaram came up with a non-trivial question, because we are putting certain condition on the function, and under that condition, a decay condition, we are characterizing a function whose Fourier transform is Gaussian, which according to us is heat kernel. Professor Sitaram's question was that how do you know that this heat kernel satisfies your estimate? If it doesn't, then you only again have the old answer that F is actually 0. And we had no idea that, what about the estimate of the heat kernel? We had absolutely no idea back then. But fortunately then Professor Yves Guivarch from France was visiting us then, and he has pointed out a paper of Jean-Philippe Anker, which appeared in 1998. The estimate of the heat kernel is actually something more than the Gaussian. You have a Gaussian factor appearing, that is e power minus alpha mod x square. This mod is actually related to the metric. Alpha has something to do with the t, but the extra factor really which appears is this phi naught. This is the Harishchandra spherical function for lambda equals to 0. This guy actually has got a half decay than the growth of the space. The space blows like e power something like e power 2r, and this has a decay like e power minus r. So this is